Very good morning, students.
Good morning, sir.
Good morning, sir.
Good morning, all of you. So, without wasting any time, let us start with the discussion. So, last class we have been studied about this carboylamine reaction, and we have seen the mechanistic approach. The primary amines will be reacting with CHCl3 in the presence of KOH to form respective isocyanates, which is also called as carboylamine reaction. And primary aliphatic and aromatic both are going to be showing this particular reaction. After that, if you go with the details, reaction with a benzene sulfonyl chloride or Hinsberg reagent. With the benzene sulfonyl chloride, how this reaction is going to happen? So, what is benzene sulfonyl chloride first of all? Benzene sulfonyl chloride is, what is benzene sulfonyl chloride, students? Benzene sulfonyl chloride is pH S double bond O S double bond O Cl. That is also called as Hinsberg reagent, and that will react with the primary amine, secondary amine, and tertiary amine to give different types of compounds. Like if you look at the Hinsberg reagent, pH S double bond O S double bond O Cl, I am doing the reaction with primary amine first. So I'll write this as pH. So finally we can include the phenyl ring. pH S double bond O S double bond O Cl. We are doing the reaction with primary amine RNH2. Same reaction, lone pair of electron present on nitrogen, that is going to be attacking the sulfur, because sulfur is less electronegative when compared to oxygen as well as chlorine, because chlorine is also withdrawing the electron density. So lone pair of electrons on nitrogen attack the sulfur. Can I directly remove the chlorine or first move the pi electron density? We have to first move the pi electron density because pi bond is a weaker bond. So movement of pi electron density you can easily indicate. So you can write pH S double bond O SO minus, sulfur is connected with the chlorine, and also new bond is formed between sulfur and nitrogen will have a positive charge, two NH bonds as it is, as well as it is connected to some alkyl group R. Now again we all know that negative charge present on oxygen is not so stable when compared to S double bond O. So negative charge comes into. Why it will be coming into easily? Because sulfur chlorine bond is also a polar bond. So chloride is going to be lost immediately. So you get a pH S double bond O N nitrogen positive charge, two NH bonds, and we have an alkyl group. And we can say the chloride which is lost in the previous step, that can be picking up this proton. Why I am calling this as a proton? Because NH electron density is moving towards nitrogen. So as soon as this proton is picked up, you get pH S double bond O NH R with only one lone pair of nitrogen. Because one NH bond has been lost, that is one proton is picked up by the Cl minus, so we form HCl. Now if you look at this particular compound, it is nothing but N alkyl. If it is just a pH S double bond O NH2, it is benzene sulfonamide. But on the nitrogen, one alkyl group is there, so N alkyl benzene sulfonamide. In this N alkyl benzene sulfonamide, if you try to add this to particular alkali like NaOH, since nitrogen and hydrogen bond are there, that is nitrogen is connected to one hydrogen, the base can be picking up this proton easily or not? Yes or no? The base has a tendency to pick up that particular proton. Why? Because S double bond O is a strong electron withdrawing group, so they want to withdraw the electron density, thereby developing the partial positive charge. So base can easily pick up this proton, so NH electron density can come into, S double bond O can be in resonance. So since NaOH, whenever it is added to N-alkyl benzene sulfonamide, in the N-alkyl benzene sulfonamide there is a acidic proton. That acidic proton can be picked up by the base. So this N-alkyl benzene sulfonamide can be soluble in alkali. The N-alkyl benzene sulfonamide is soluble in alkali because NH bond is there. If you try to do the reaction with secondary amine, in the same way, you get NR plus HCl. That means N, N dialkyl benzene sulfonamide. Here, the secondary amine reacts with Hinsberg reagent. That reaction is going to happen, but the product, whatever we are going to get, that product is not going to be soluble in alkali. It is insoluble in alkali. The secondary amines will be reacting with Hinsberg reagent to give an insoluble N, N dialkyl benzene sulfonamide, whereas tertiary amine do not react. Primary, secondary react. Primary amine will react with Hinsberg reagent to form N-alkyl benzene sulfonamide, which is going to be soluble in alkali. Secondary amines react with benzene sulfonamide, like benzene sulfonamide, benzene sulfonyl chloride, that is Hinsberg reagent, to form N, N dialkyl benzene sulfonamide, which is insoluble in alkali, whereas tertiary amine do not react. Is that clear or not?
Yes.
Yes, right. Same mechanistic approach for primary, secondary, and tertiary as well. Hinsberg reagent is used to test between primary, secondary, and tertiary amine, because primary amine is giving a different product which is soluble in alkali. Secondary amine, different product which is insoluble in alkali. Tertiary amine, no reaction happening. These days, benzene sulfonyl chloride is replaced by para-toluene sulfonyl chloride. Instead of simple C6H5 S double bond or S double bond or Cl, you can place an electron donating group also. CH3 is an electron donating group by hyperconjugative effect, because it is present with respect to S double bond O, S double bond O Cl. With respect to this, CH3 is at the para position. So at the ortho or para position, it can show hyperconjugative effect. So because it's an electron donating group, where the removal of chlorine can be easy. Okay, so nowadays that is even replaced by para-toluene sulfonyl chloride. The amine that reacts with Hinsberg reagent to give an alkali insoluble product. Alkali insoluble product means which amine?
Secondary.
Secondary amine. So we have to just choose the secondary amine. Which one is secondary amine? First option NH, second option tertiary, third option NH2 primary, fourth option NH2 primary. Okay, secondary amine. Reaction with nitrous acid HNO2. This reaction we have seen earlier, if you remember. Where we have seen this reaction?
Phenyl.
Phenol preparation, right? Yes.
Yes.
Or NH2, if you try to react with HNO2, whenever we have NaNO2 in the presence of HCl or HNO2, we have to understand that NaNO2 plus HCl means the H plus can be reacting with NO2 minus to form HNO2. This HNO2 will have this type of structure, N double bond OH. This HNO2 can be reacting with again H plus ion. Lone pair of electrons on oxygen can attack the H plus. As soon as they attack, we will generate N double bond O, oxygen with only one lone pair, two OH bonds and a positive charge. So that will immediately release the water to form N double bond O with a positive charge of nitrogen and H2O, which is nothing but nitrosonium ion. Nitrosonium ion. So this is the electrophile generated whenever NaNO2 and HCl or simply HNO2. HNO2 directly given, not an issue. NaNO2 plus HCl, NaNO2 plus any acid like H2S4. Then also you have to do the same thing. Nitrosonium ion is going to be obtained. RNH2 plus N double bond O with a positive charge of nitrogen. R I am placing here. Lastly, we can also replace with phenyl group. If I place phenyl, then I'll be getting benzene diazonium salts. If I place R group, then simple alkyl diazonium salts are going to be obtained. So lone pair of electrons on nitrogen, they attack the nitrogen. Lone pair of electron present on this nitrogen of the amine, primary amine, will be attacking the positively charged nitrogen of nitrosonium ion. Will be generating what? RNH2, R2 NH bonds, positive charge on this nitrogen, and nitrogen single bond and double bond oxygen. And oxygen as it is has two lone pairs. Nitrogen, double bond oxygen, and oxygen has two lone pairs as it is. Now can I say NH bond is going to be polar bond, and Cl minus is lost in the reaction mixture. Cl minus can easily pick up this proton. NH electron density can be given to nitrogen, generating R, NH, nitrogen having lone pair, N double bond O, oxygen having two lone pairs. Oxygen possessing two lone pairs that can be easily attacking the proton, forming R, NH, one lone pair of nitrogen, nitrogen single bond, double bond oxygen. Oxygen has only one lone pair and one OH bond and a positive charge on oxygen. Now positively charged oxygen is unstable, it is attracting the pi electron density. So lone pair of electron present on this nitrogen will come into the N double bond O, pi electron density moves away, generating what? R, NH, positive charge, N double bond N, oxygen, two lone pairs on nitrogen and NH bond. Again, Cl minus picks up the proton. NH electron density is given to nitrogen. You will generate R. Nitrogen regains the lone pair. N double bond N. Oxygen, 2 lone pairs. Again, it is going to be attacking the H plus. Lone pair of electrons and oxygen attack the H plus. You will form R. Nitrogen lone pair N double bond N. OH2 plus you will get with only one lone pair on oxygen and a positive charge. Lone pair of electrons and nitrogen come into water leaves. So you generate R N triple bond N with a positive charge on this nitrogen, and this nitrogen has the lone pair as it is, and H2O is lost. R N triple bond N, like R N2 plus, this will be having electrostatic force of attraction with Cl minus. R N2 plus Cl minus is going to be obtained. Diazonium salts are obtained. Diazonium salts are obtained whenever primary amines are going to be reacting. You can also write the respective resonating structure. How to draw the resonating structure of this? Like if you can write this, the pi electron density you can include Rn. Nitrogen can have the lone pair, double bond. The other nitrogen will be having a positive charge. Like this also I can write the structure or not? This lone pair I can include in resonance. If the structure is written as R N triple bond N, the center nitrogen will be having a positive charge. If it is written as R N double bond N, the terminal will be having a positive charge based on the similar resonating structures. Right? Primary aliphatic amine RNH2 react with NaNO2 in the presence of HCl, forming ROH. They have formed directly ROH, but we have seen the reaction up to RNH2 treated with a NaNO2 HCl forms what? R N triple bond N plus Cl minus. This is what we have seen. But R N triple bond N plus, that can be undergoing loss of N2 easily. A slight increase in temperature. This is going to be formed. The isonium salts are going to be stable only below 5 degrees Celsius. With above 5 degrees, immediately the N2 gas is going to be released, forming a carbocation. That carbocation can be attacked by the lone pair of electrons and oxygen present from water, leading to the formation of RO, oxygen only one lone pair, two OH bonds, and a positive charge. Immediately loss of H plus can occur, forming ROH. So alcohols can be formed. This is one of the possibility. Carbocation is formed actually. Now I have attacked with the lone pair of electron present on oxygen, but I can also do the attack of chloride ion to form respective RCl. I can also do the elimination to form respective alkenes. Yes or no? Based on the set of products, you have to decide, like if all the alcohols are given, which is the major alcohol, like that you have to choose. If all the alkyl halides are given, then among the type of alkyl halides, which should be major. How to decide major? Carbocation is obtained, so rearrangements are possible. Rearrangements are possible. Okay. So NaNO2 in the presence of HCl gives HNO2 plus NaCl. So that will be giving nitrosonium ion. RNH2 plus nitrosonium ion. So here you can see carefully. Earlier we have written the structure as R N triple bond N with a positive charge on middle nitrogen, because that center nitrogen is connected to 4 bonds, so it has lost the lone pair. But you can write the same resonating structure in this manner: R N double bond N, because this pi electron density can move away. This is diazonium ion, which is highly unstable. Why this is highly unstable? Because it has a tendency to undergo the cleavage and release out the N2 gas. N2 gas is highly stable because of a triple bond between two nitrogen atoms. N2 gas is highly stable because of a triple bond between two nitrogen atoms, and it is also increasing the entropy of the system, and it is a gas. So obviously that removal of N2 is very high, and formation of carbocation will be very easy. So this will be easily attacked by a nucleophile like a water. Yes or no? R plus and N2 is obtained. That will be attacked by water. Lone pair of electrons and oxygen attack the carbocation to form ROH2 plus. Loss of H plus occurs. You get a respect to alcohol, which will be the major. But if alcohols are never given in the options, they have given all alkyl halides, then you have to choose the respective alkyl halide only based on the substitution, nucleophilic substitution. Is that clear, students?
Yes, sir.
This is also used as a test for primary aliphatic amines. Primary aliphatic amines will be leading to the formation of respective diazonium salts, which are highly unstable, thereby forming carbocations. Carbocations will be attacked by the nucleophiles like water to form the respective alcohols. So this is the reaction shown by primary aliphatic amine. If you take aromatic amine, what you will get? You will get benzene diazonium salt. Okay. If you take pH, like aniline, you take pH NH2, treating with NaNO2 and HCl 0 to 5 degrees Celsius, it forms what? Benzene diazonium salt, N triple bond N plus Cl minus. And this benzene diazonium salt will be showing different categories of reactions. And what is the importance of this benzene diazonium salt is benzene diazonium salts are they are also unstable. You may ask a question, sir, if the diazonium salts are unstable, then why we are preparing them? Why we are preparing them is a very interesting question, because they are useful to place a nucleophile on the electron rich phenyl ring. Because the phenyl ring, if you look at, the phenyl ring also has the 3 pi bonds, which is already electron rich. Placing a nucleophile on the electron rich benzene ring is not easy. Yes or no? That's why we are, if you want to do the nucleophilic aromatic substitution from the alkyl halide, just remember how much high temperature we are maintaining, how much high pressure we are maintaining. Anyone remembered or not? Like I have taken a
Yes, sir.
chlorobenzene. Chlorobenzene we have taken. If I treat that chlorobenzene with NaOH, no reaction will occur under normal conditions. If I want to do the reaction, I have to maintain the temperature to be around 600 Kelvin, 300 atmosphere pressure. And the reaction is going to be happening easily only when we have electron withdrawing groups at ortho and para positions. So there are a lot of difficulties, because why the carbon halogen bond cannot be broken and the phenyl ring is already electron rich, nucleophile is electron rich. How can you place an electron rich substituent on already electron rich substrate? That is not possible. But whenever you choose this path, because N2 gas is releasing easily, this phenyl cation is obtained. I'm not supposed to write this phenyl cation in this manner directly. I'm not writing a positive charge here and a phenyl cation, but you can think of nucleophile can easily come as the N2 can leave. Yes or no? Nucleophile can easily come. Like same, you can do nucleophilic aromatic substitution by addition elimination type. Nucleophilic aromatic substitution by addition elimination type. But here the loss of N2 can be easy, not as hard as in the alkyl halides. So that is why it is a very good path to actually substitute a nucleophile or an electron rich species on a already electron rich benzene ring. That is why these are highly famous in the organic chemistry. Like ROH plus H plus will be giving ROH2 plus, RNH2, NaNO2 plus HCl, RN2 plus. Like a similarity they have given, but that is not a correct meaning, because we all know ROH plus H plus will be just obtained by lone pair of electrons on oxygen attacking the H plus. But here nitrosonium ion is formed. With the help of nitrosonium ion, we are doing the reaction, and you are having Rn triple bond N with a positive charge on metal nitrogen. CH3, CH2, CH2, and NH2, NaNO2, HCl, you will get what? CH3, CH2, CH2, N2 plus. That will undergo loss to form a carbocation. What type of carbocation it is? Primary carbocation. There can be a possibility of rearrangements. Whenever the carbocation is formed, you have to do the rearrangement. Rearrangements you are doing. So 1, 2, hydride shift you have done. 1, 2 hydride shift you done. From the primary carbocation to the secondary carbocation, you get a more stable carbocation. Now that more stable carbocation is going to be attacked by water. Yes or no? It is not, OH minus is not there in the reaction mixture. Water is acting as a nucleophile that will be attacking the electrophilic carbon of the carbocation, and ultimately you will get the secondary alcohol as the major product, like 2-propanol, CH3, CHOH, CH3, that will be the respective major product. Is that clear?
Sir.
Yes,
Yes,
sir.
right. Very good. Primary aromatic amine, if you do the same reaction with the primary aromatic amine, like aniline, NaNO2 HCl, 273 to 278, that means 0 to 5 degrees Celsius only. You will be getting benzene diazonium salt. If you try to increase the temperature up to 10 degrees, you will get phenol, because this N2 can be cleaved easily and H2O will be acting as a nucleophile that will attack. if the temperature of the diazonium salt solution is allowed to rise up to 283 Kelvin, as I was saying, up to 10 degrees, the salt gets hydrolyzed to phenol, because if the temperature is high, the loss of N2 will be, because this bond can be even easily cleaved. Secondary aromatic amines will give what? Secondary aromatic amine, like if you take this particular compound, N, NH, NR, yes or no, and we have lone pair of electrons and nitrogen. This is a secondary aromatic amine. NH group is there, one side alkyl group, the other side aryl group. You are now going to treat this with NaNO2 HCl. NaNO2 HCl means what? NaNO2 plus HCl means the electrophile generated is nitrosonium ion, N double bond with a positive charge of nitrogen. N double bond with a positive charge of nitrogen. What is going to happen now is lone pair of electrons and nitrogen will be attacking the positively charged nitrogen of N double bond plus. You generate this particular compound, NH bond as it is, NR bond as it is, nitrogen will have a positive charge now. Yes or no? NH bond as it is, NR bond as it is, nitrogen will have a positive charge, and nitrogen forms a new bond with the other nitrogen, N double bond O. And we have chloride ion which was present in the reaction mixture that can easily pick up this proton. NH electron density comes into, and you get nitrogen, alkyl group, nitrogen regains the lone pair, N double bond O with the two lone pairs on oxygen. And remember students, if you try to attack this particular lone pair of electrons on oxygen with the H plus, like if you want to continue further, yes or no? Like earlier also we have continued the same reaction. Nitrogen will have lone pair, NR group is present, N double bond O, oxygen will have one lone pair, one OH bond and a positive charge. And if you try to write the respective resonating structure, lone pair of electrons and nitrogen comes into, pi electron density moves away, you will generate NR positive charge nitrogen, double bond N, OH. Yes or no? Oxygen regains the lone pair. Now look at the species. This positively charged nitrogen, it is unstable here. N double bond, NR, N phenyl group. There was no hydrogen connected to nitrogen, which can be easily picked up. There is no hydrogen connected to nitrogen. If we have NH bond, then only that can be picked up by chloride ion. They're regenerating the lone pair of electrons and nitrogen, but it is going to be highly unstable. The positively charged nitrogen with N double bond N alkyl group, N phenyl group will be highly unstable, and that is why these reactions are not going to be initiated. So the reaction will stop it here only. So we'll get what? pH NR N double bond O. Okay. So we cannot say lone pair of electrons on oxygen attack. So because when compared to this particular compound, this is unstable. So this is not happening. So we'll get they are unstable, and this is the major product. So what is the major product now? N alkyl. On the N group we have alkyl. N alkyl. On the N nitrogen atom we also have nitroso. N alkyl, N nitroso, aniline. If you have simple NH2, it is called as aniline. If you have simple NH2, it is called as aniline. But this hydrogen is replaced by one alkyl group. This hydrogen replaced by one N double bond group. So N alkyl, N nitroso, aniline. That is going to be the correct name of the product. This is aniline. And yellow oily liquid is going to be obtained. So whenever you treat a particular unknown compound with a NaNO2 in the presence of HCl, if you try to do the diasterization, and in that case, if you are getting an yellow oily liquid, then you have to say that particular unknown substance is a secondary amine. That particular unknown substance is a secondary amine. Is that clear, students?
Yes, sir.
Right. Tertiary amines will have what type of reaction? Tertiary amine. Try to think of. If we have tertiary amine, like if the first reaction happens, lone pair of electron nitrogen attacked in NO plus. Like if you have tertiary amine, tertiary aromatic amine, I'll take N R dash R double dash. So lone pair of electron nitrogen, if I am trying to attack to NO plus, there should be at least one hydrogen connected to nitrogen, which can be lost. But is that available?
No.
The hydrogen is not there, right? We have R dash, R double dash, nitrogen will have a positive charge. We get N double bond O with a positive charge, positively charged nitrogen. This has been lost. So this is going to form Again, this particular positive charge nitrogen is going to be unstable. So this is unstable because nitrogen is not connected to any NH bond, so it is not going to be stabilized. So what happens in this case? Lone pair of electron present on nitrogen that is not attacking the N double bond or electrophile. Rather, what happens is electrophilic substitution occurs because lone pair of electrons on nitrogen, they were electron donating into the ring, right? The phenyl ring. They increase the electron density at ortho as well as at para positions. So, or it's a nitrogen connected to two alkyl groups with a lone pair of electron nitrogen. That is a electron donating group which increases the electron density at ortho and para positions. At ortho and para positions, electron density is going to be increased. So out of ortho and para, which is going to be substituted by N double bond?
Para.
Para, because of minimum steric repulsions. Okay, to maintain minimum steric repulsions, you will get Nr2 as it is, pH as it is, but N double bond O, that is electrophilic substitution occurred. Here what happened? Electrophilic substitution occurred. Substitution occurred, and it is a electron donating group. So ortho para directing. Ortho para directing group. Right? Right, students. Then let us look at some chemical reactions of diazonium salts. Diazonium salts, if you try to observe carefully, the diazonium salts are going to be obtained whenever aniline has been treated with NaNO2 in the presence of HCl. There are two categories of reactions. The first category of reactions of diazonium salts is where the N2 group is replaced. That means you get a phenol or halobenzene or benzene or nitrobenzene, like that. N2 group is going to be replaced. In the second set of reactions, the coupling reactions, where the N2 group is not replaced, where the N double bond and diazonium group, diazo group is going to be replaced, or you will get azodized systems. So aniline treated with NaNO2 in the presence of HCl 273 to 278 Kelvin, you will get benzene diazonium chloride. Chemical reactions of benzene diazonium chloride are two categories. Reactions involving displacement of nitrogen, that means where N2 group is going to be lost, and reactions involving retention of diazo group. Reactions involving displacement of nitrogen and reactions involving retention, that means N2 is not lost. So these are the two category of reactions which you need to understand. Yes or no? So let us look at the reactions. Reactions involving displacement of nitrogen, like benzene diazonium salt. This benzene diazonium salt can be treated with a Cu2Cl2 in the presence of HCl, Cu2Br2 in the presence of HCl, CuCN in the presence of HCN. In all the cases, what happens? This N2 gas can be leaved, and this particular carbon, which will be electrophilic in nature, that will be attacked by the chloride ion or bromide ion or cyanide ion. So chloride or Br minus or Cn minus. The nucleophile is going to be substituted. In the first case, you can get chlorobenzene. Second case, you can get bromobenzene. Third case, you can get cyanobenzene. That means you are going to have the nucleophile getting substituted on the phenyl ring. Nucleophile getting substituted on the phenyl ring. And these set of reactions, what are those called as? Sandmeyer reaction. That is benzene diazonium salt treated with the Cu2Cl2 in the presence of HCl, Cu2Br2 in the presence of HBr, CuCN in the presence of HCl, forming respective chlorobenzene or bromobenzene or cyanobenzene. That is nothing but your Sandmeyer reaction. We can also do the reaction with Cu in the presence of HCl and Cu in the presence of HBr. If you take metallic copper in the presence of HCl or copper powder in the presence of HBr, you can have same products again. Chlorobenzene, like Cl minus is acting as a nucleophile, attacks the electrophilic carbon. Br minus acts as a nucleophile, attacks the electrophilic carbon. Chlorobenzene and bromobenzene obtained. And this reaction is called as
Gatterman reaction.
Gatterman reaction. Gatterman reaction or Gatterman-Koch reaction?
Gatterman reaction.
What is Gatterman-Koch reaction?
Benzaldehyde.
Benzaldehyde will be obtained. Like remember the names also, like from benzene, CO plus HCl in the presence of Cu2Cl2. For the replacement of we have done the replacement of diazo group with a chloride and a bromide, but with to replace iodine. we have to take Ki instead of Cu2 Cl2 and Cu2 Br2. In the presence of Ki, where we will be getting K plus and I minus ion, this requirement is not sufficient. Like we don't require any Cu powder or Cu2 Cl2 or copper in the plus 1 state. Directly the I minus can be attacking this particular electrophilic carbon, leading to the formation of iodobenzene. Fluorobenzene you will get whenever you treat with a fluoroboric acid first. Whenever you treat with fluoroboric acid, the benzene diazonium chloride N2 plus Cl minus, that is going to be treated with the HbF4. HbF4 will have H plus and Bf4 minus. That Bf4 minus ion will be developing electrostatic force of attraction with N2 plus. So N2 plus Bf4 minus ion you will get. Yes or no? C6H5 N2 plus Bf4 minus you will get, right? That N2 plus Bf4 minus, whenever you try to heat it, you will be generating what? Whenever you try to heat it, you will be generating fluorobenzene and N2 gas is released. Along with that, Bf3 is obtained. Okay. HbF4, if you treat with N2 plus Bf4 minus obtains, that benzene diazonium fluoroborate. Upon heating, you will get fluorobenzene. If you are heating, obviously this carbon nitrogen bond is going to be broken and you have a tendency for the release of N2 gas, and fluoride is going to be attacking this particular species and Bf3 is going to be lost again. So this is how the fluorobenzene, iodobenzene, chlorobenzene and bromobenzene can be obtained. Treatment with HbF4 followed by NaNO2 and heating. That will be producing NO2. This is nothing but Ball-Simon reaction, like production of fluorobenzene. Like N2 plus C6H5 N2 plus Cl minus treated with HbF4, you get a benzene diazonium fluoroborate, which is stable at room temperature and water insoluble. If you treat that with NaNO2 in the presence of copper and heating, you will be generating NO2 minus ion that is going to be placed, generating respective nitrobenzene. Na plus NO2 minus is there, right? That NO2 minus is now going to be placed on the electron-rich benzene ring. You will be having the respective nitrobenzene obtained. So understand this sequence. Benzene diazonium chloride treated with HbF4, you will get benzene diazonium fluoroborate. This benzene diazonium fluoroborate just heating generates fluorobenzene. Benzene diazonium fluoroborate heating in the presence of NaNO2, you will generate nitrobenzene, right? And if you try to treat this benzene diazonium chloride, like if you simply heat it in the presence of H2O, what is the product you expect?
Phenol.
Phenol you will get. And you can also treat that with milder reducing agents. Reducing agents will themselves undergo oxidation, like H3PO2 in the presence of H2O or C2H5OH. You will generate respective benzene plus H3PO3, like H3PO2 has been converted to H3PO3. C2H5OH, ethanol has been converted to ethanol. So they undergo oxidation. Okay, they are reducing agents because they are undergoing oxidation. So benzene diazonium chloride will be undergoing these set of reactions. These are all the combined reactions of benzene diazonium chloride. Sandmeyer reaction, Gattermann reaction, treatment with Ki to form iodobenzene, treatment with HbF4 further heating forming fluorobenzene, Ball-Simon reaction, treatment with HbF4 followed by NaNO2 and copper heating, getting nitrobenzene. Simple heating of benzene diazonium chloride generates phenol. Treatment with the milder reducing agents forms respective benzene and H3PO3 in the case of H3PO2, CH3CHO, ethanol in the case of ethanol. These are all the reactions where you can see the displacement of nitrogen happening. These are all the reactions where you can see the displacement. The N2 group has been displaced. We can also have other reactions where N2 group is not displaced. What are those reactions? The N2 group is not going to be displaced. Reactions involving retention of diazo group. These are nothing but electrophilic substitution reaction is going to happen. Coupling reaction of benzene diazonium chloride is an electrophilic substitution reaction. Like if you can think of the benzene diazonium chloride resonating structure, like N triple bond N with a positive charge of nitrogen. If you try to draw the respective resonating structure, this pi electron density moves away. You get a phenyl group in this fashion. N double bond N plus. This is your respective electrophile. This you can treat with a aniline, or you can also treat with phenol. You will be generating different types of azo-dyes. Like if you treat with a phenol, phenol is acidic in nature already. So that is why you have to maintain the pH 10 to 11. In the basic medium, you have to do the reaction. If you are treating with aniline, aniline is a base, so you have to do the reaction in the weakly acidic condition. So treat the benzene diazonium chloride with phenol. What is going to happen? Phenol is an electron donating group. Electron donating groups are ortho para directing group. So this is your ortho substitution, and this was your para substitution. So where the electrophile is going to be substituted? On the para position, obviously. Yes or no? Because of minimum repulsions. What is the electrophile? This is the electrophile where nitrogen possesses a positive charge. So C6H5 N double bond N, positively charged nitrogen, that is electrophilic nitrogen, attacked at the para position. C6H4OH plus H2O, which is para hydroxyazobenzene. On the para position, you have a OH group. So para hydroxyazobenzene, which is also called as an orange dye. If you try to repeat the reaction with the aniline, again you are going to have para aminoazobenzene, which is an yellow color dye. Whereas in the case of phenol, you are having an orange color dye. That colors you have to remember, students. Is that clear or not? Benzene diazonium chloride reacts with the aromatic compounds containing strongly activating groups like OH, NH2, NHR, NR2. These are strongly activating groups. With OH and NH2, the reactions has been seen. With OH, you will be generating para hydroxyazobenzene, which is actually an orange dye. With NH2, you are generating para aminoazobenzene, which is an yellow color dye. So these are the different sets of reactions where you can have the benzene diazonium chloride, where the diazo group is retention and the diazo group is like replaced. The N2 group has been replaced or it is retained. In the two conditions, we have seen the different sets of reactions. With amino, you have the yellow color dye. With phenol, you have the orange color dye. Try to figure out what are A, B, C, and D. What is A? Benzene, HNO3, H2S4.
Nitrobenzene.
Nitrobenzene. Nitrobenzene treated with tin in the presence of HCl.
Aniline.
Aniline. NaNO2 HCl. Aniline.
Benzene diazonium.
Benzene diazonium chloride N2 plus Cl minus. CuCN HCN.
Cyanobenzene.
Cyanobenzene. Very good. Then comes the next category, that is electrophilic substitution reactions. Electrophilic substitution reactions are going to be happening with respect to aromatic primary amine, that is aniline you can take. So if you take aniline, aniline is a very good electron donating group. What are the reactions which you are going to expect here? I have said the same thing in alcohol also, if you remember. Like phenol. Phenol, if you treat with the Br2 in the presence of CS2 or CCl4, what type of product you get? If you treat phenol, treat with the Br2 in the presence of CCl4 and Br2 in the presence of H2O. You get different types of products or same product?
Different product.
So first case, what you will get, Fatima?
Ortho bromophenol.
Ortho, like ortho para directing, you will get ortho and para, out of which ortho will be major or para will be major.
Ortho will be major.
Why?
Intermolecular hydrogen bond.
Is that present? Look at the bromine here. No, right?
No.
Whereas in the case of Br2 in the presence of H2, like intramolecular hydrogen bonding is not present, right? Bromine is there here. Whenever you have phenol treated with Br2 in the presence of CCl4, you will get a ortho product and para product. Whenever you treat phenol with Br2 in the presence of H2O, you will get what?
Tribromo.
All the three positions are also occupied by bromine. But in the case of aniline, whether it is Br2 in the presence of CS2 or CCl4 or Br2 in the presence of H2O, you will be getting 2,4,6 tribromo aniline only, which is a white PPT. because NH2 lone pair of electrons on nitrogen. Nitrogen is less electronegative when compared to oxygen, so it is a very good electron donating group. It is electron donating group. OH is also electron donating group. Both are donating electron by mesomeric effect. But NH2 is a very strong and good electron donating group, thereby increasing the electron density and ortho and para positions greatly. So you'll get 2,4,6 tribromoaniline, which is the white PPT is going to be obtained. So that is what you can see in the halogenation of aniline reaction. And why in the case of in the case of a non-polar solvent, what is going to happen? The polarity in bromine is only induced by electron density of the aniline. Like because of NH2 is a strong electron donating group, the Br2 is actually polarized. Lewis acid is not required first case, because NH2 and OH are a very good electron donating group. Lewis acids are not required. Also, if you look carefully, NH2 is a very strong electron donating group, so it can polarize Br2 greatly such that it will lead to the formation of 2,4,6 tribromophenol in the case of non-polar or polar solvent. But with OH, in the case of non-polar solvent, only phenol is actually electron donating group. So phenol is only responsible for the polarization in Br2. And since OH is a less electron donating when compared to NH2, it will only lead to the formation of monosubstituted product. But if you take phenol and OH group in the presence of Br2 and H2O, H2O is a polar solvent which can also polarize Br2. H2O is a polar solvent which can also polarize Br2. Thereby, you will be getting the tribromophenol, 2,4,6 tribromophenol. That's what with respect to phenol. If you do the reaction in the non-polar solvent, you will get the para will be the major product because no intramolecular hydrogen bonding based on less repulsions, we have to say. And phenol treated with Br2 in the presence of H2O, you get 2,4,6 tribromophenol. But with respect to aniline, in the presence of Br2 non-polar solvent or polar solvent, you get 2,4,6 tribromoaniline only. Is that clear, students? Halogenation of aniline, no Lewis acid required. Non-polar solvent or polar solvent, you get the halogenation happening at all the three positions, like ortho, both the ortho and para positions. Right. How to prepare monosubstituted aniline derivative? Like I want this. How can I do? From the aniline, I have to just get only para bromoaniline. How can I get this? How to prepare monosubstituted aniline derivative? Like aniline is a very strong electron donating group without any Lewis acid. If you take Br2 in the presence of a non-polar solvent or a polar solvent, it doesn't matter. It is getting 2,4,6 tribromophenol. Now what I am going to do is, why it is getting tribromo product? What is the reason? What is the reason?
highly activates the benzene ring.
Yeah, NH2 is activating the benzene ring and it is a very good electron donating group. So what I am going to do is, I will decrease the activating tendency of NH2. NH2 is a very strong activating group. It is electron donating group. It is activating the ortho and para positions greatly. So if I control the activity, obviously the substitution is going to be controlled or not? Yes or no, Nandana?
Yes, sir.
So how can I control the activity?
In acidic medium.
In acidic medium, if I do the acidic medium, then you will get unlinear ion. If you get unlinear ion, it will be meta-directing. It is also strongly electron withdrawing group, meta-directing group.
Acetylation.
Acylation, very good. So if I do the acylation, it will be protecting group as well, thereby decreasing the electron density. First to do the aniline, treat with CH3COCl pyridine. If you treat with CH3COCl, what happens? NH2 is going to be converted to NHC double bond of CH3. So if you look at the acylation now, lone pair of electrons present on nitrogen, they were not only in resonance with the phenyl ring, but they are also in resonance with the C double bond group. So net electron density coming into the phenyl ring has been decreased. So it is not strong electron donating group now, because its a lone pair has been shared between C double bond O as well as the phenyl ring. C double bond O as well as the phenyl ring. So you get first acetanilide or N-phenyl ethanamide is going to be obtained. This N-phenyl ethanamide, if you try to do the bromination now, Br2 in the presence of CH3COOH, what is going to happen if you do the bromination now? It is still ortho para directing group, but out of ortho and para position is going to be substituted because ortho positions are automatically protected or not. Ortho positions are not substituted here because of repulsions between the NHC double bond of CH3 and the incoming electrophile. Due to that repulsions, ortho position is actually protected. So it is acting as a protecting group also. You have protected the ortho position when you try to acylate the respective aniline. You have only substitution happening, electrophilic substitution occurring at a para position. And now acylation occurred. From that acylation, if I want to get the aniline back, like NHC double bond of CH3, you don't require. You have only NH2 required. You can treat that with H plus in the presence of H2, acidic hydrolysis. If you do the acidic hydrolysis, what will happen? If you do the acidic hydrolysis, NHC double bond of CH3, first you treat with H plus, lone pair of electron present on oxygen, they will be attacking H plus. As they attack the H plus, we have to increase the electrophilicity here. We have to increase the electrophilicity of the carbon because H2 is a weaker nucleophile, and also this lone pair of electron nitrogen in resonance. So partial positive charge, electrophilicity of the carbon has been reduced. Electrophilicity of the carbon has been reduced. So I have to do the acidification. NHC double bond O, oxygen only one lone pair, OH bond and a positive charge, and CCH3. Now H2O comes into the reaction mixture. H2O, lone pair of electron present on oxygen, they will be attacking the carbon. C double bond of pi electron and moves away. What happens in that case? NH, lone pair of electrons and nitrogen. C, oxygen only one lone pair, two OH bonds, positive charge. CCH3, oxygen one lone pair, two lone pairs OH bond because it regains the electrons. Can I say lone pair of electron present on nitrogen, they can pick up the proton? I'll write this as pH as of now. pH. Lone pair of electrons present on nitrogen, they can easily pick up this proton. They can easily pick up this proton. As soon as they pick up, you will get what? pH group connected to nitrogen, nitrogen connected to two NH bonds. Nitrogen bears a positive charge, also connected to carbon, carbon connected to oxygen, two lone pairs. Another carbon connected to same oxygen connected to two more oxygens. COH, COH, and CCH3. This positively charged nitrogen is unstable, it withdraws the electron density, so lone pair of electrons and oxygen comes into this CN electron density is given, generating PHNH2. Nitrogen regains the lone pair. Along with that, you will generate CH3, C double bond O, OH, and you have positive charge oxygen OH bond. This will undergo loss of H plus, generating CH3, C double bond O, OH. Okay, PHNH2 is obtained. So do the acylation first, then do the electrophilic substitution with the Br2 in the presence of a CH3COH, then do the acidic hydrolysis. Acidic hydrolysis of respective N substituted amides will lead to the formation of amines. You will generate NH2, 4-bromoaniline is going to be obtained. Is that clear, students? 4-bromoaniline is going to be obtained whenever you do the acidic hydrolysis as well.
Yes, sir.
Yes, sir.
Let us do the nitration. If I do the nitration of aniline, what are the products I am going to expect? If I do the nitration of aniline, what are different types of products I will be expecting?
So para, ortho, and metal.
Trinitro
Trinitro,
aniline.
okay. Why, Faizan?
Sir, because nitrosonium ion is obtained from HNO3 and then ion is strong electron donating group.
Okay. And the trinitrobenzene is going to be unstable slightly because of repulsions. And what is going to happen is we also have lone pair of electrons on nitrogen. They will pick up the proton or not because this is an acidic medium. HNO3, H2S4. Aniline is a base. Acid-base reaction occurs. So you can generate the anilinium ion also. Anilinium ion is electron donating or electron withdrawing?
Withdrawing.
Electron withdrawing by resonance or inductive effect.
Inductive.
Inductive only, not resonance. It can't, the pi electron density cannot move. Okay, if it moves, nitrogen will have 5 bonds around itself. So it is electron withdrawing by inductive effect. Electron withdrawing group by inductive effect. Now look at the scenario. NO2 plus is the electrophile generated. That NO2 plus can be substituted ortho position or para position with respect to NH2. But since NH3 plus can be obtained in a greater amount because H2SO4 and HNO3 both are acids present, so strong acidic medium is there. So if you can think of that, you will be writing the respective ortho product and para product. Out of ortho and para, which you will write major? Out of ortho and para,
Ortho.
ortho you will generally write major. Why? Due to intramolecular hydrogen bond.
Hydrogen bond.
But that is not happening in reality. In reality, para will be the major. After that, you will have meta. The least is going to be the ortho. So ortho you will have only 2%. Para you will be having 51%, whereas meta you will have 47%. This percentage, with respect to this percentage also you have to understand. In reality, the process of nitration of aniline, we get the major as para, then meta, and the least will be ortho. The reason is NH2 will be attacking the H plus ion, and NH2 as it attacks the H plus, it will be forming NH3 plus, which is a strong electron withdrawing group by inductive effect. Because it is a strong electron withdrawing group, it will be initiating the meta direction. And also the NH3 plus formation is greater, and it is not going to be allow the incoming electrophile to come at the ortho position. Due to inductive effect and the resonance effect, we can say the para is going to be the respective major product. And due to the formation of unlinium ion, meta will be the respective major product. And after that, least is going to be a respective ortho substituted product. Yes or no? The least
Yes,
will be ortho substituted product. So whenever you have aniline treated with H plus, you will be getting the respective unlinium ion. Unlinium ion will be meta directing. If you have aniline treated with the CH3COCl in the presence of pyridine, like if you want to generate again ortho substrate product or only para substrate product, in that case what you can do? In that case, again you can apply the logic of, again you can introduce the logic of acylation, like NH2 can be converted to NHCOCH3. Like acylation you have done to the respective aniline, you will be generating acetanilide. Yes or no? That phenyl N-phenyl ethanamide, if you treat with the HNO3 in the presence of H2SO4, now the unlinium ion is not going to be obtained easily. Rather, the electron donating tendency has been decreased. So it is again ortho para directing. Out of ortho and para substitution will be measured due to minimum electron repulsions. So you get NO2 substitute the para position, NHC double bond or CH3. If you try to do the acidic hydrolysis, finally you will be generating NO2 and NH2. This is the respective major product. Like if you want to get only para nitro aniline, in that case again you have to choose the path of acylation. Whatever the path you are choosing, acylation path, that acylation path is actually acting as a protecting group. It protects the ortho position. It will not make the electrophile present at the ortho position. And meta substitution is also decreased because unlinium ion is not formed. So you will be getting the para as the major product. Got it or not? If you do the simple nitration, of aniline, you will be getting mixture of ortho, para and meta. Out of all those, ortho will be the least, para will be the major, and meta will be the second major, like 51-47. Only you will be getting para major, then you will have meta. The ortho will be least. Yes or no? This can also be, you can understand by the inductive effect of NH3 plus. Similarly, if you do the sulfonation of aniline, sulfonation if you are doing, aniline you are treating with H2SO4. H2SO4 will be having H plus and HSO4 minus ion. And aniline is also a base, so it can be reacting with acid directly to form salt first. With the sulfonation reaction, if you want to do lone pair of electrons and nitrogen, they can pick up the proton, forming unlinium ion. So unlinium hydrogen sulfate is going to be formed. In the first case, what will happen? NH3 plus HS4 minus unlinium hydrogen sulfate will be formed. Whenever you try to heat this unlinium hydrogen sulfate, then only electrophilic substitution is going to happen, where the SO3 is going to be substituted at the para position. Like SO3H group present at the ortho NH2, with respect to NH2, ortho position of SO3H will be having more electronic repulsions. So whenever you heat the unlinium hydrogen sulfate up to 453 to 473 Kelvin, in that temperature range only you will be getting on the para position SO3H is substituted, which is called as sulfonilic acid, which is also called as sulfonilic acid or para aminobenzene or sulfonic acid. With respect to NH2, para position is going to be SO3H substituted. This you can again convert like lone pair of electrons on nitrogen, like sulfonilic acid is this one, NH2, lone pair of electron present on nitrogen, S double bond O, S double bond O, OH. Lone pair of electrons present on nitrogen, they can pick up the proton. OH electron density can be given to oxygen, generating what? Generating NH3 plus S double bond O, S double bond O minus, which is nothing but a zither ion or not? You remember the zither ions? The acidic group and basic group present in the same molecule, they are going to be reacting with each other to form the respective dipolar species, which is a nothing but zither ionic form. The sulfonilic acid or para amino benzene sulfonic acid, with respect to SO3H only we have to name, because it is not a substituent of aniline, it is a substituent of sulfonic acid. On the para position you have amino group, so para amino benzene sulfonic acid, that will be existing in the zither ionic form, because acidic group and basic groups will be reacting with each other, and you have a dipolar systems. Is everything clear, students, so far?
Yes, sir.
Yes.
Okay, sulfonation we have done. And does aniline show Friedel-Crafts reaction? Aniline do not show Friedel-Crafts reaction, that is alkylation and acylation. The reason? If you take aniline, treat with AlCl3, because Lewis acid and aniline is acting as a Lewis base, acid base reaction is going to happen, which will be forming lone pair of electrons on nitrogen, they will be attacking the aluminium. So NH2, nitrogen will have a positive charge, AlCl3 with aluminum negative charge. Okay, this species is going to be formed, which is a deactivating group. Yes or no? It is not activating towards the Friedel-Crafts reaction, because AlCl3 has to be a Lewis acid which has to generate the electrophile, but instead of generating electrophile, it is reacting with the substrate aniline. So if it is reacting with the substrate aniline and forming a deactivating group towards the electrophilic substitution reaction, so that is why it will not undergo, aniline will not undergo Friedel-Crafts alkylation or acylation reactions because of this deactivating group. Yes. And last comes reduction of nitrobenzene. Okay, here the mechanisms are not required. You have to just remember the equations and understand carefully. Nitrobenzene you treat with Fe in the presence of HCl, tin HCl, H2 in the presence of palladium. What you will generate?
Aniline.
You will generate aniline directly. If you treat nitrobenzene with zinc in the presence of NH4Cl, what you will generate? NHOH group is going to be present. Okay, different types of reactions. In the first case you will get aniline. In the second case, zinc in the presence of NH4Cl, you will get NHOH. NHOH is going to be substituted. In the third case, Fe and H2O, again N double bond O is going to be present. That is N double bond O. The nitro group will be converted to N double bond O, similar to nitrosonium ion. Electrolytic reduction, dilute H2SO4 if you do. In the nitrobenzene in the presence of dilute H2SO4, electrolytic reduction, what happens? You will generate aniline. In the case of concentrated H2SO4, you will again generate the same species as obtained here with the zinc and NH4Cl. That is C6H5 NHOH. That C6H5 NHOH will undergo rearrangements. It will undergo rearrangements where OH group is going to be shifting to respective para positions. You will form respective para amino phenol. Okay, so that rearrangement is going to happen. You will generate the respective para amino phenol. Is that clear, students? These reaction mechanisms are not required. So just remember these equations, like you already know the first one with respect to different other sets like zinc and NH4Cl, Fe and H2O, electrolytic reductions. Electrolytic reduction of nitrogen in dilute H2S4 produces aniline. In the presence of concentrated H2S4, you will get a C6H5NHOH, which rearranges to form para-aminophenol. Right? So these are the different concepts which you can understand from respect to nitrogen and its compounds. So just a second. So this will be covering up or completing your organic chemistry, like major parts. Then the next topic which you are going to discuss is biomolecules. Okay, it is not directly organic chemistry, but the concepts are useful. The next 3 chapters: biomolecules, polymers, chemistry in everyday life. After that, environmental chemistry. All these are, you know, right? They are most theoretical in nature as well as application is oriented. So whatever the linkages we are going to discuss in biomolecules, or whatever the types of monomers we discuss in polymers, and different examples in each category, and what are the analgesics, tranquilizers, antibiotics, which we are going to discuss in chemistry in everyday life. You have to understand them and you have to also remember them. Okay, I'm not forcing you to remember this stuff. That is not the way of teaching. But you have to understand the chemistry. But ultimately, if someone asks you a question like what is the linkage present in starch, we can't derive it, right? Can you derive the linkage? Like what type of linkage is present in starch, if you remember?
1,4-glycosidic linkage.
How do you know,
Alpha 1,4.
Faizan?
Sir, biomolecules chapter you studied in bio.
No, that's okay. But how do you know? Like why only
Remember,
1,4?
I have to.
So we have to know it because it is the fact. So whatever the linkage is present in that particular biomolecule or a polysaccharide, we have to analyze it experimentally. Okay, science is all about understanding the nature, not creating something new. We have to understand how nature is working. So if you try to study or look at that particular starch molecule at the microscopic level, where you can understand the type of linkages, the 1,4-glycosidic linkage is happening. The C1 of alpha D glucose units linked with the C4 of beta D fructose. Beta D fructose or alpha D glucose only, right? C1 of alpha D glucose with C4 of alpha D glucose. So like that, only alpha D glucose are there and C1 C4 linkage is happening. So that you have studied experimentally and you have observed, that is the result. You may ask a simple question, sir, why not 1,3? Why not C1 C3 linkage is happening? Why not means that is how the structure is actually. Okay, that is how the structure of biomolecule is actually. So you understand the chemistry as well as you need to remember some facts. That is what I want to say. So let us start with the new chapter. Biomolecules. Biomolecules means what? Biomolecules, like whatever the organic reactions you are going to do, whatever the organic reactions we have done so far, starting from your nomenclature, isomerism, optical activity, after that hydrocarbons, GOC1, GOC2, haloalkanes, alcohols, phenols, ethers, carbonyls, carboxylic acids, amines. From all these, we have done a lot of chemical reactions, organic reactions. But similarly, inside our body also there are a lot of organic molecules. We call them as biomolecules, where their reactions will be having a particular biological response. Because of that biological response only we are living. So what are we, who are we means we are just chemical creations. We are present here, I am teaching here, like I want to deliver some concept. I have trained my mind in such a way such that I have to deliver this much amount and in this particular way. At these particular points we have to raise the topic. In these particular points I have to go into detail. So all those points I have already prepared. Like I have already understood what I am going to deliver today. Like you are also prepared, like you have to sit for 1.5 hours and you have to listen to this particular lecture. You are training the mind. That means automatically the reactions are happening inside the body. So all those reactions which are happening inside the body, every activity, whatever we are doing is actually controlled by different biomolecules. Okay. So biomolecules are nothing but the macroscopic molecules, which are again organic molecules with a lot of heteroatoms, and whose reactions are producing a biological response, and every biomolecule will be having a different type of biological activity. Okay. Biomolecules are chemical compounds which are building blocks of life and perform important functions in living organisms. Okay, this is the basic way of saying they are the building blocks of life. Yes, that we know. That means every biomolecule will be having a different types of reaction, will be having a different type of activity. And if you try to classify the biomolecules, the most important categories: carbohydrates, proteins, enzymes, vitamins, nucleic acids, and hormones. And you will be discussing about these in your 12th standard. So let us start with carbohydrates. What are carbohydrates? Carbohydrates, earlier they were found to be hydrates of carbon. Like carbohydrate, the name has been given that way only. Carbohydrate. Carbon, hydrate means water. Initial days, the compounds which are found to be the hydrates of carbon, they are called as carbohydrates. But there are some molecules, like they should be having the molecular formula CxH2O taken Y. It is a hydrate, it is a carbon, hydrate of carbon. The compounds which are called as hydrate, the compounds which are falling under this formula, they are called as carbohydrates in the initial days. But what happened is there are many molecules which are falling in this particular category. There are some molecules like acetic acid, CH3COH. What is the formula? C2H2O taken 2. Yes or no? C2H4O2, I can write as C2H2O taken 2 or not? So can I write this as, can I say this as a carbohydrate? Yes, it is fitting into the formula. If you go with the formula only, carbohydrate name hydrates of carbon. If you go with the formula only, acetic acid is fitting the formula, but it is not a carbohydrate. And there are some carbohydrates which are not fitting into the formula. The initial definition of carbohydrates is hydrates of carbon, that is molecules which are having the formula CX H2O taken Y, CxH2O taken Y. But now what is going to happen is CxH2O taken Y is the molecular formula given to the carbohydrates, but the logic here is there are molecules which are not fitting into this particular formula even though they are carbohydrates. There are molecules which are fitting into the formula even though they are not carbohydrates. Carbohydrates, carbon and water. Simple ratio you get CHO 1:2:1. Glucose will be having a molecular formula of C6H12O6. Glucose we have C6H2O taken 6. Sucrose we have a molecular formula of C12H22O11. That is C12H2O taken 11 times. That is your sucrose. General formula of carbohydrate can be written as CxH2O taken Y. Here, hence they are called as hydrates of carbon, and that's why the name. Exceptions: Remnose C6H12O5 is a carbohydrate, but it does not fit into the formula. Remnose C6H12O5 is a carbohydrate, but does not fit into the formula. Acetic acid is not a carbohydrate, but is fitting into the formula. So the initial definition of carbohydrates, which is called as hydrates of carbon, is not justified. It is not justified. So we have to redefine that particular definition. The initial definition of carbohydrate, which are called as hydrates of carbon, is not justified throughout. So we have to redefine that particular definition. New definition of carbohydrates. What was the new definition? The carbohydrates are optically active polyhydroxyaldehydes or ketones. They are carbohydrates. What are those? Optically active polyhydroxyaldehydes and polyhydroxyketones, or compounds which give such compounds on hydrolysis. Like you can have a compound A which is optically active polyhydroxyaldehyde. You can have a compound B which is optically active polyhydroxyketone. You can have a compound C which upon hydrolysis gives optically active polyhydroxyaldehydes or polyhydroxyketones. Then they are called as carbohydrates. This was the correct definition. It is not the hydrates of carbon, but still with the old definition only the name has been assigned. Carbohydrates. Why the name has been assigned as carbohydrates? Hydrates of carbon. But that definition is not valid throughout for all the category of molecules. Original definition of carbohydrates is carbohydrates are optically active polyhydroxyaldehydes or polyhydroxy ketones or compounds which develop or which produce polyhydroxy aldehydes or ketones are called carbohydrates. Only dihydroxyacetone is optically inactive carbohydrates. Dihydroxyacetone. We have acetone is CH3, C double bond or CH3. Dihydroxy on this particular carbon, if you substitute OH, on this particular carbon, if you substitute OH, CH2OH, C double bond or CH2OH, that is nothing but your dihydroxy acetone, which is nothing but optically inactive carbohydrate. All carbohydrates are optically active except this one. Is that clear, students? The initial definitions?
Yes.
Yes, sir.
Carbohydrates are also called as saccharides. Greek word saccharin means sugar because they are sweet in taste. Classification of saccharides on the basis of their behavior on hydrolysis. Classification of saccharides on the basis of their behavior on hydrolysis. Like classification of saccharides, you can say monosaccharides, oligosaccharides, polysaccharides. Monosaccharides means what? Monosaccharides.
Only one unit of carbohydrate.
Oligosaccharides means
6 to 10 units of carbohydrate.
6 to 10. What happened to 2 to 5?
2
So you said 1 unit in monosaccharide, 6 to 10. What happened to 2 to 5? Faizan? That's not there, no? So monosaccharide means a carbohydrate that cannot be hydrolyzed further to give simpler unit of polyhydroxyaldehyde or ketone, that is said to be monosaccharide. That is the simplest sugar is the monosaccharide. Like you can have about 20 monosaccharides are known to occur. Glucose, fructose, ribose, all these are monosaccharides. Monosaccharides are the simplest sugar units. They will not be undergoing hydrolysis further to form respective simple sugars. They are the simplest sugars. Oligosaccharides are carbohydrates that yield 2 to 10 monosaccharide units on hydrolysis. They are said to be oligosaccharides. If you are getting 2 units, it is said to be disaccharide. If you are getting 3 units, trisaccharide, 4 units, tetrasaccharide. Like that, up to 10 units, we can call them as oligosaccharides. More than 10 units, if you are getting, it is said to be a polysaccharide. Okay. They are further classified as disaccharide, trisaccharide, and tetrasaccharide, depending upon number of monosaccharides which produce on hydrolysis. Sucrose is obtained by glucose and fructose. Maltose is obtained by glucose and glucose. Like different disaccharides obtained by different types of monosaccharides. And we'll be studying about whatever the disaccharides we have in our syllabus and what are the linkages, whatever the polysaccharides we have, what are the linkages, all them we'll study in detail. This is a basic introduction. After oligosaccharide, you have polysaccharide. Polysaccharide means which are giving very high number of monosaccharide units upon hydrolysis. Carbohydrates which yield a large number of monosaccharide units on hydrolysis, they are said to be polysaccharides. Example, you can say starch, cellulose, glycogen, gums, all these are coming under this category. Starch, cellulose, glycogen, gums. Classification of saccharides on the basis of this reaction. This classification understood, right? Monosaccharide, oligosaccharide, polysaccharide.
Yes.
Yes.
Yes, right. Next classification is the on the basis of nature of reaction. We can call them as reducing sugars or non-reducing sugars. Reducing sugars means what? Reducing sugars means
We
yeah,
have
they
a free hand, so they can.
they reduce failing solution and tolerance reagent. Reducing sugars are those which can reduce failing solution and tolerance reagent. All monosaccharides and disaccharides in which aldehydic and ketonic group are free behave as reducing sugars. They reduce the failing solution and tolerance reagent. What is the condition? Next condition: all monosaccharides and disaccharides all monosaccharides are reducing, all polysaccharides are non-reducing. In the disaccharides, wherever you have free aldehyde group or ketonic group, they are called as reducing. In the disaccharides, if we do not have any free aldehydic or ketonic group, it is said to be non-reducing. Got it or not? All monosaccharides, all mono reducing, all poly non-reducing. Disaccharides reducing and non-reducing, can be reducing and non-reducing. What do you mean by reducing? We have
Having free higher than keto.
free carbonyl group. Okay, no free carbonyl. Okay, this is the condition. So they are all reducing sugars. They can reduce failing solution and tolerance reagents. All monosaccharides and disaccharides in which aldehydic and ketonic groups are free, they are known as reducing sugars. Glucose, fructose, maltose, lactose, they are all reducing sugars. Is that clear?
Yes, sir.
Yes.
In fructose, what type of carbonyl group is present?
Ketonic.
Ketonic.
Ketone.
Can ketonic group reduce failing solution and tolerance reagents?
No.
No,
Then why
sir.
you are categorizing that in reduced sugar?
So methyl ketones can reduce.
Alpha hydroxyketones, not methyl ketones. Alpha hydroxyketones can be showing tolerance reagent, right? If you look carefully.
Yes, sir. Yes, sorry.
Yes. Alpha hydroxyketones, they can undergo tautomerization where they can be forming the respective aldehyde groups, and thus they can be used as reducing sugars. So you don't get confused, like reducing sugars means they are reducing failing solution and tolerance agent, but how can fructose be included even though fructose has ketonic group? Because fructose is an alpha hydroxy ketone which can undergo the respective tautomerase structure to form aldehyde group, which can still reduce the failings and tolerance. So that can be also categorized as reducing sugar. Non-reducing sugars means all polysaccharides and disaccharides in which there was no free carbonyl group. They do not reduce failing solution and tolerance reagents. All polysaccharides and disaccharides in which aldehydic or ketonic group are bonded, they behave as non-reducing. Sucrose, starch. Sucrose is a disaccharide which will be behaving as a non-reducing sugar, because in sucrose we have 1,2 linkage. There was no free carbonyl group. There was no free carbonyl group available, right? After that, you can have the question like compound that deviates from the carbohydrates classification is
Acetic acid.
acetic acid. Polysaccharide is glucose, sucrose, starch, fructose.
Starch.
Okay, these are very simple questions from the concepts whatever we have studied so far. So monosaccharides, then classification. After the monosaccharides, oligosaccharides, polysaccharides, and then looking at reducing and non-reducing sugars, we can look at monosaccharides and do the classification of them. Classification of monosaccharides is based on number of carbon atoms and functional groups. Number of carbon atoms and functional groups. So you can just to try to classify them. So number of carbon atoms, if the functional group is aldehyde, then they are called as aldoses. If the functional group is ketone, then they are called as ketoses. Number of carbon atoms 3, tri, 4, tetra, 5, penta, 6, hexa, like that the name is going to be changing. Aldose, and how many carbons are there? 3. Aldo triose, which is a glyceraldehyde is an example. 3 carbons, aldose group means present means aldo triose. 3 carbons, ketose present means keto triose. 4 carbons, tetrose, like 4 carbons means tetrose, and aldehyde group means aldo tetrose. 4 carbons, ketose means keto tetrose. 5 carbon means aldo pentose, keto pentones. 6 carbon means aldo hexose, keto hexose. 7 carbon means aldo heptose and keto heptose. So these are the different types of classifications based on the number of carbon atoms and based on the type of functional group present. Number of carbon atoms 5, and it is a ketonic group. So keto pentose, ribulose is an example. Okay, so 4 carbons, tetrose, like aldehyde group is present. So aldo tetrose. So erythritol is an example. Out of all the monosaccharides in our syllabus, we will be studying the details of only two, that is glucose and fructose, and their structures and their reactivity and their everything. Everything about those monosaccharides we are going to study. First one is glucose. Glucose is the most naturally abundant sugar and mostly found in human blood, grapes, and that is why it is also called as grape sugar, honey. Okay, these are the sources from which you can actually have abundant of glucose. That is why glucose is also called as grape sugar. Glucose, if you try to study, you have to look at the preparation of glucose first and the structural analysis of glucose. First, if you try to prepare glucose from the laboratory method, how to prepare glucose? Laboratory method and commercial method. If you go with the laboratory method, from the sucrose, that is from the cane sugar, sucrose which is having a dextro rotation of plus 66.5, when you do the acidic hydrolysis of sucrose, when you do the acidic hydrolysis, what is going to happen? The sucrose upon acidic hydrolysis will be giving glucose and fructose. Sucrose upon acidic hydrolysis, sucrose upon acidic hydrolysis gives glucose and fructose. This is the method of preparation of glucose, but again you have an issue here. Sir, you are getting a mixture of products. That was a question you can raise. Sucrose upon acidic hydrolysis is giving glucose and fructose, but how to separate glucose from the fructose? How can we separate that, students? Acylation I cannot do. Acylation where I have to do, Fatima? Understanding the logic or not? In the sucrose we have two monosaccharide units. I am doing the acidic hydrolysis. So whatever the glycoside linkage we have in sucrose, that is going to be cleaved and you're getting glucose and fructose. This glucose and fructose, whatever you have, they are present in the mixture, in the reaction mixture. We have to separate them. How to separate them? On hydrolysis, the sucrose changes the sign of rotation from dextro to levo. That is why it is called as invert sugar. Yes, if you look at the hydrolysis of sucrose, sucrose is dextrorotatory plus 66.5, glucose is dextrorotatory plus 52.5, fructose is levo minus 92.4. So average, if you take average, you are having plus of 52.5 plus of minus 92.4 whole divided by 2, which is again negative in nature or not? The average
Yes.
optical rotation of glucose and fructose is negative, whereas sucrose is positive. So sucrose, if you do the hydrolysis, the positively like dextrorotatory compound, which can rotate the plane polarized light in the clockwise direction, that is changing its optical sign. That is why it is called as invert sugar. On hydrolysis, sucrose changes the sign of rotation from dextro to levo. Levo means you may ask a question, sir, sucrose is also giving glucose, which is dextro again. You have to take the average optical sign of glucose and fructose, that will be negative. That is levorotatory. Sucrose is dextrorotatory. So this change in optical sign, that is said to be, because of that it is called as invert sugar. Separation of glucose and fructose. So how to separate it? While cooling, alcohol is added to the reaction mixture. Glucose crystals are removed by cooling, like we are doing the crystallization. Crystallization means what? We have the reaction mixture, like this is a solution where I have glucose and fructose both. I have glucose and fructose both are there, and I am just cooling it down. Like I am cooling the saturated solution of glucose and fructose. In the process of cooling, I am adding alcohol. The alcohol has been added. Alcohol. Glucose being insoluble in alcohol crystallizes out first. Why? In the glucose, you have like R C double bond H group, C double bond H group, whereas in the fructose, you have R C double bond R dash groups. Like ketonic group is there in fructose, glucose aldehyde group is there. In the fructose, both the alkyl groups are electron donating groups, which will be moving the pi electron density greatly towards oxygen, developing more partial negative charge on oxygen. Because of more partial negative charge on oxygen, it will be developing new intermolecular force of attraction with hydrogen. Hydrogen present on the alcohol. Yes or no? ROH is an alcohol. From the alcohol, whatever the partial positively charged hydrogen is there, that will develop more electrostatic force of attraction with the ketonic group present in fructose. But the glucose is going to be having less interactions, lesser intermolecular forces developed. Understood this point or not? I have a saturated mixture of glucose and fructose. I am adding alcohol. In the alcohol, which is soluble? Fructose being more soluble in alcohol. Why? Because it developed more intermolecular force of attraction with alcohol. Glucose less soluble. Glucose being less soluble in alcohol, it will be remaining as a precipitate. That means crystals of glucose will be separated out at the or settling down at the bottom. So in a solution of glucose and fructose, whenever I am doing the crystallization, whenever I am cooling it, whenever I cool it, crystals are going to be formed. Yes or no? Whenever you make a sweet at your home, whenever you are heating that particular sweet, like we call it as pakam, yes or no? At higher temperature, it will be in the liquid state. But as you cool down the temperature, what do you have? The
It's solid.
crystals come out. The same thing happened. The glucose and fructose are soluble at high temperature. Now I am cooling it. If I am cooling it, solubility is reduced. Solubility is reduced. So slowly I'm also adding alcohol. So in the alcohol, fructose is more soluble when compared to glucose. So all the crystals of glucose come out. Since the crystals of glucose come out, they can be separated by filtration or not. Yes or no?
Yes, sir.
So same thing, while cooling, alcohol is added to the reaction mixture. Glucose crystals are removed. Why not fructose? Because fructose is more soluble. Glucose being insoluble in alcohol crystallizes out first. Crystals of glucose are separated by filtration. Fructose being more soluble in alcohol remains in the solution. This is how you can separate the glucose and fructose. And sucrose is said to be invert sugar because it is changing the optical rotation whenever it has been done the hydrolysis. Is that clear?
Yes, sir.
Yes, sir.
Yes, right. The commercial method. Commercial method is from the starch. If you take starch, we know starch also contain the alpha D glucose units. And if you do the hydrolysis of starch in the acidic medium at a temperature of 393 Kelvin and pressure of 2 to 3 atmosphere, you will get glucose. Like in the sucrose, if you do the sucrose hydrolysis, you are getting glucose and fructose. Again, I have to do the separation of glucose. But if I do the hydrolysis of starch, I will be getting directly glucose only, no fructose. I'm not getting fructose. So that is why starch, from the starch, if you do the acidic hydrolysis, whatever the glucose is getting, so that is going to be pure and there are no needs to actually purify it. So that is why it is a commercial method and not the laboratory method. In the commercial scale, we don't complicate the things. We want the product at the easiest way and it has to be easily purified, like cost effective. All these points you have to take into account whenever you're looking at the commercial point of view. It's not like I want to prepare glucose from very complicated way. The preparation itself costs some very high amount. Then to whom you are going to sell that particular glucose? Yes or no? So commercial way depends upon always cost effective things. So we'll discuss the purification. Purification of glucose means whenever you have a colored impurities. Yes or no? Although glucose is obtained, whenever you have a colored impurities, the colored impurities are removed by adding activated charcoal. Why? What happens whenever you try to add the activated charcoal? Adsorption occurs. So whatever the colored impurity you are going to have, that all the colored impurities, they are going to be adsorbed on the surface of activated charcoal. Therefore, that particular activated charcoal can be removed out again by filtration. That is how you can do the purification of glucose. In the purification, if whatever the colored impurities are there, they can be removed by adsorption. And glucose crystals are removed by cooling. The same, whenever you try to cool it down, you will be having more solubility of respect to glucose. If since glucose more solubility of fructose than glucose, since fructose is more soluble in the case of laboratory technique, what is going to happen? You can separate that glucose from the fructose. But here we are only having glucose. So whenever you are lowering the temperature, obviously glucose crystals are obtained. They can be settling down at the bottom, so they can be easily filtered out. Okay, students. So chemical reactions of glucose and all we'll study in the next class. Okay, the details like what type of structure is there and how that structure can be understood. Thank you all, everyone. Bye.
Thank you.
Thank you, sir.
Thank you, sir.